Okay, so the next speaker is Harun on the formalization of a proof calculus for incremental linearization for satisfiability modulo nonlinear arithmetic and transcendental functions. If you're ready, you can start.
Yeah. Hi, everyone. Welcome to my talk. I'm Harun, and today I'm going to present a work formalizing proof calculus for... Okay, sorry guys. Yeah, so we're presenting a formalization of proof calculus for incremental linearization for satisfiability modulo nonlinear, real arithmetic, and transcendental functions. And this is joint work with a bunch of my colleagues at Stanford University and UFMG and University of Iowa. So the motivation is SMT solvers are used in many safety-critical applications, and many of them require the theory of nonlinear real arithmetic or transcendental arithmetic, like, for example, for dynamical systems or digital signal processing. And here by transcendental functions, we mean trigonometric functions and the exponential function. So there are many use cases of those functions and reasoning thereof. And then typically reasoning in these theories, nonlinear real arithmetic, NRA, and nonlinear transcendental arithmetic, NTA, is done through this process called incremental linearization. And so we decided to formalize the CPP'26 implementation of incremental linearization in Lean. And in the process, we identified errors and missing hypotheses in the documentation, as well as mismatches between the documentation and the CPP'26 code base. And in addition, we also successfully reconstruct these proof rules using the Lean SMT tactic. So that's our contribution. So first, let me explain what incremental linearization is. So yeah, you have nonlinear and transcendental functions, as I mentioned before, such as like the exponential function or trigonometric functions. And so what we do is we abstract these away as uninterpreted functions, and then we incrementally approximate them using linear bounds. So this doesn't guarantee termination. It could, just run, but it's a scalable alternative if you don't need exact solutions. Like, for example, in the figure below, you have like this nonlinear object circle, and the question is whether the intersection of the circle and the squares are non-empty. And instead of just looking at the circle, you can approximate it using four lines and conclude that those lines don't intersect the circle or the squares. Incremental refers to, in the process, we could get better linear bounds as necessary. So that's incremental linearization. Now, the background we use for our formalization relies heavily on MATLAB, mainly for real numbers. We also use a decimal approximation of pi to 20 decimal places, and I'll speak more about that later. We use the properties of the exponential and sine functions. And earlier in the talk, I said trigonometric functions, but really the proof calculus only deals with the sine function because other trigonometric functions can be expressed in terms of sine. Like, for example, cosine is just a phase shift of the sine function, and then tangent is just sine divided by cosine. So we just focus on exp and sine. We also use derivative libraries And we use Taylor polynomial theorems and also theorems about convexity. So now let's talk about the proof rules. There are 21 of these rules, and we could put them into 3 broad categories: inequalities, and then properties of sine and exp, and bounding pi, so trigonometric, and then finally bounding transcendental functions using Taylor polynomials. And for most rules, we prove a lean theorem that encapsulates the rule. But for some other rules, we write a tactic. Like, for example, there's a rule that bounds pi, and we have a lean tactic that does this. So let's go over each of these categories one by one. So for inequalities, for example, one of these rules is, so you have the multiplication of 2 variables bounded above by a tangent plane. And this is just equivalent to the following like linear conditions. And then similarly, you have the other version of the rule where the product of 2 variables is bounded below by a tangent plane, and you can replace that by some linear inequalities. So to prove this rule is more or less straightforward. We encapsulate it, we formalize in lean just as is in the proof rule, and we prove it using like nlinearith or any tactic that deals with inequalities. So here's an example of another rule. This one, you consider monomials, and you have, you know whether these variables are positive or negative, and then the question is whether the product of the variables are positive or negative. So like, it's better to see an example. So like, for example, A is positive, B is negative, C is negative, and the question is whether a squared times b cubed times c cubed is negative. And so this can be done by this tactic we wrote called arithmetic sign, which basically applies these theorems iteratively to the monomial expression. And so these theorems are just all possible cases of raising a negative number to an odd power, a negative number to an even power, and so on and so forth. Yeah, this is an example of a rule where instead of like writing a theorem, we have a tactic that applies theorems iteratively. Cool. And now, so now the second set of rules, which is about the properties of sine and bounding pi. So one example is a sign shifting theorem, which basically, so we always, in the proof calculus, we always want to work in the interval negative pi to pi, because we're using an approximation of pi. And so if we're too far from the origin, the error compounds. And so it's best to just stick to the interval negative pi to pi, which works in the case of sine because it's a periodic function. So this interval is enough to express everything. So for example, the proof rule is given any variable y, I can find like a principal value of x in the interval negative pi to pi such that sine of x is sine of y. And in lean, we express this just as it's stated in the proof rule. And then very quickly, I could just go over the proof of how this works. So in lean, if we're already in the desired interval, then there's nothing to do. Otherwise, you consider shifting your variable. If x is greater than pi, then you shift x down to the interval negative pi to pi using this expression, the ceiling of the quotient of x minus pi over 2 pi. And then we just use a math loop theorem that says, if you add an integer multiple of 2 pi, sign does not change. So that's the main crux of the proof. And if x is less than negative pi, we just do the same thing, a similar thing. And then the next rule we're talking about is bounding pi. So this is needed for, like, again, for the convexity of sine, for example. And so the rule says, given bounds L and U, whether is pi between L and U. And to do this, we actually use norm num, and we use an approximation of pi in MATLAB that's approximated to 20 decimal places. So if your L and U are like smaller than this interval, or like inside this interval, which is like within 10 to the negative 20 of pi, then the tactic will incorrectly fail. So like one thing that we could do for future work is improve this approximation so that this interval size decreases. And finally, the third set of rules, which is bounding transcendental functions by Taylor polynomials. So the idea is to use Taylor approximations as linear approximations to this sine function and the exponential function. So the main theorem we use is the Lagrange form of the Taylor remainder theorem, which basically says if you have any function f whose differentiable and has its nth derivative is differentiable in this interval, then f minus the nth Taylor polynomial is this remainder expression. And so this is in MATLAB, but there's a caveat, and that it has this extra assumption that x is greater than x0, and in half of our rules we actually need x to be less than the starting point. In particular, for Maclaurin expansions, you need x to be less than 0, and so first we needed to extend this rule to to remove this assumption, basically for x being less than x0. And the way we did that was we took this theorem and we instead applied it to f of negative x, and then we have like a bunch of like rewrite theorems that basically push negation signs into and out of Taylor expansions and into and out of derivatives and nth derivatives and so on. So we first extended the Taylor mean remainder Lagrange theorem to remove that assumption, and then here's an example of one of the rules that use this theorem. So for example, if I have exponential x of t is bounded below by the Maclaurin of the exponential function. And so this is for both when x is positive and x is negative. And this is how we state it in lean. And so in the first case, if t is positive, then here p of t is the is the Taylor polynomial. So we look at the difference and we apply the theorem in MATLAB, Taylor mean remainder Lagrange, and we examine the expression we get at the end, and we just have to prove that that's positive. And then for negative t, we need the other version of the theorem, and once we use that, we get a similar expression to study once you do the difference between the exponential function and the Taylor polynomial. And then finally, one last example would be bounding the sine function from below on the negative real numbers. This is one of the rules where the documentation was ambiguous, and so we had to propose a theorem. And so this is what we proposed, where d is the degree is 1 above a multiple of 4, and then you can bound sine from below by the Taylor polynomial, where D is 1 mod 4. So in the process of formalizing 21 rules, we found some errors and missing hypotheses. The first example is like there were some missing side conditions. So for example, one of the rules had a missing condition that T is bounded above. And then some rules just had incorrect or some ambiguous assumptions on the degree, which we had to correct. So like, for example, the one I showed just on the previous slide, and a similar rule for approximating below on positive numbers. So to test our formalization, we do proof reconstruction, which, so lean SMT is a tactic that from lean you can call CVC5 to generate a proof. And then you replay that proof step by step using a process called proof replay. So CVC5 proofs are replayed in lean in the form of lean theorems and tactics. And so in order for this process to work correctly, we need to ensure that the proof rules in CVC5, there is a corresponding proof rule in lean, and these are all saying the same thing. So the formalization was mainly to extend lean SMT for NTA and NRA reasoning. But there were some challenges encountered. The first being mismatch of proved rules in CVC5 output. So partially because the documentation in some cases was ambiguous, but also we had to refine our theorems to actually match the CVC5 code base. And then another issue that we ran into was computing a polynomial at a specific value is not possible. So we had to, in lean, so we had to define computable versions of polynomials. Like for example, this is how we define the exponential Taylor function, and then prove equivalence to the Taylor polynomial of the exponential function as already defined in MATLib. And then finally, if L and R are real numbers, it's impossible to decide whether L is less than R because real numbers are not computable in lean in the general case. But in most of our cases, L and R are rational numbers, so we're okay. And then in the one case where L or R is pi, we use a 20-point decimal approximation, which can be improved upon as future work. Okay. So finally, here are some future directions. CVC5 sometimes fails to add casting steps, so there's a challenge when mixing integer and real values in mixed integer real valued proofs, and this leads to holes in the proof. And so this would require work at the solver level to ensure the casting steps are added for these like mixed integer real valued proofs. And then the second would be sometimes there are unjustified reasoning steps performed by the solver that creates holes in leans, and then again this would require working at the solver level with the CVC5 team to ensure these holes are patched up. And that's all for my talk, and I'd like to take questions.
Could you say a bit about what proportion of proofs produced by CVC5 you're able to actually reconstruct? Or did you say that and I missed it? Right,
so we're able to reconstruct each and every one of the proof rules we formalized as part of this proof calculus. But we, like on like other benchmarks, so we have like our own benchmark, and we construct everything on it. Some like standard benchmarks, they don't use these rules, so yeah, we didn't use it. We didn't, yeah.
Am I correct that in CVC5 all numbers are in the same type? Do in CVC5, is there a difference between real numbers and other numbers? Are pi and 5 in the same type?
So, I mean, you could declare them as real numbers, yeah.
So that makes that all your formulas are mostly manipulating real numbers.
So, I mean, I guess you could also declare 5 as an integer, yeah, yeah.
Your problem of missing castings is because
yeah,
of this difference.
Yeah, because there are like some integer steps and there are real number steps too, and so like in Lean, I guess we need like casts between these types, yeah. But in CVC5, it just reasons like fluidly through all of these.
They're all numbers.
Yeah.
Yeah. Well, I think you can also try to work in the proof system in such a way that you use mostly real numbers and you mark the ones that happen to be integers or rational numbers as a subsets instead of being in a different type. So that would make it possible to remove the need for casts.
Yeah, that's an interesting suggestion. I think, I think like just manipulating real numbers is in Lean that's challenging because they're not computable. But yeah, that's something we could certainly think about. Yep. Okay.
Thank you for